So next up, we have John Keller, who will be presenting on halos, hydrogen, albedo, lunar observations from the surface.
All right, thank you. So I'll begin by acknowledging the listed co-investigators and by stating the obvious that the solar wind is 95% hydrogen, and hydrogen is one of the two elements that compose water. The solar wind is an important contributor to space weathering alongside other processes such as micrometeorite impacts. In many ways, hydrogen in the solar wind drives the chemistry of space weathering. What is HALOS? HALOS is a two-instrument suite for measuring solar wind ions and backscattered ions and neutral particles from the surface. The goal of HALOS is to determine the dynamics of the lunar hydrogen volatile cycle, specifically obtain the backscatter proton and hydrogen outflow from the local lunar surface as a function of local time and temperature, quantify the signatures of the putative diurnal migration of hydrogen products and determine their origin, and also derive any space environment effects on anomalous escape of hydrogen. Next slide. So this chart illustrates various aspects of the lunar water and hydrogen cycle. Early speculation was that hydrogen ions in the solar wind could directly form water when combined with oxygen in the lunar regolith. This hasn't been observed in the laboratory experiments at solar wind energies. However, the formation of OH, hydroxyl bonds, by solar wind energy ions has. Furthermore, the hydrogen implanted into the regolith sets conditions for subsequent water formation by energetic processes, such as micrometeorite impacts, and this has been observed in the lab by simulating with the laser micrometeorite impacts. Solar wind hydrogen maintains the chemically reducing conditions of the lunar surface that drives the formation of nanophase iron and enables subsequent formation of larger microphase iron. And it's worth pointing out that the formation of nanophase iron is not favored thermodynamically, but the reaction is driven forward by saturating the surface with implanted hydrogen. Next slide. So the payload of HALOS consists of two instruments, ion and energetic neutral atom spectrometers. The ENA analyzer is a top hat style geometry and is equipped with an electrostatic ion rejector, keeps the charged particles out. And it has charge conversion surfaces. The principle of operation is that neutral atoms enter the instrument and encounter a Venetian blind array of charged conversion surfaces at grazing incidence. Upon charge conversion, they enter the electrostatic analyzer when the energy and direction can be determined.
2 minutes, John.
Thank you. The IMS also takes advantage of the top hat layout, but includes deflectors on the entrance to enable scanning out of plane and a gated time of flight for mass discrimination. Each instrument would be mounted so that the sputtered and reflected particles from the surface could be observed. Because of their cylindrical symmetry, the analyzers will also measure simultaneously incoming particles from the zenith direction. HALOS requires little in the way of bandwidth, as the table below demonstrates. And if you move to the next slide, in terms of resources, so that's the bottom table on the left, it's relatively small, which will enable co-manifested instruments that complement HALOS, such as additional plasma instruments or pursue distinct scientific goals. Little development work is needed as there's significant heritage in the instruments that have been done, or we have lab demonstrations at appropriate environmental conditions. Finally, HALOS is landing site agnostic, capable of making important measurements anywhere on the moon, at least where the solar wind can get to. And we certainly have additional or increased interest in around polar regions and lunar swirls.